Thanks, Stephanie. Although I'm tempted to argue with you, I won't. So just hold back. Yeah. Yeah, it's the first time anyone's ever introduced me as the coolest phonologist. But I'll take it. That's fine. I think this stuff's really cool, and I hope you do too. And I'd like you to interrupt me with clarification questions as we go along. We'll save the I think it's better to save the discussion for after. But if there are things that you simply don't understand, please let me know. Because I know you come from a wide range of backgrounds, and I'll do my best. But yeah. So this is joint work with Jennifer Culbertson, who's in Edinburgh, Coral Hutto, who's a student at UMass currently, and Robert Stubbs, who's just graduated from UMass recently. So when generative linguists are modeling typology, and by modeling typology I mean they're creating systems that can represent any of the worlds. I just remember this camera, can I go this far? No. That's a shame. So I'm stuck from here to about here, right? Okay. I can come as close as I want. Yeah. Okay. When generative linguists are modeling typology, they're creating systems that can represent any linguistic system found amongst the world's languages. That's the goal. But also, they want these systems not to be able to represent things that are not found cross-linguistically. So the goal is to create a system that generates all and only the possible languages of the world. And when generative linguists are doing this, the way they're doing it is by creating a theory of universal grammar. They're creating a grammatical system that can either represent a type of language or not. And they're testing these predictions against the languages that they find cross-linguistically. When generative linguists are doing learning research, that is creating models of learning, it's just so tempting to go this way, I'll try to resist. When they're creating computational models of learning, what they're trying to do is create learning models that will find a correct grammar in the space of all possible grammars given some set of linguistic data. The learning theory in this approach doesn't actually play any role in modeling typology. The modeling of the typology is done by creating a theory of UG, and then the learning theory is just explaining how kids can learn the language in given some amount of data. A very different approach to the relationship between cross-linguistic data, grammar, and learning is the iterative learning approach to language that was pioneered by Luke Steels, Bart de Boer, Simon Kirby, etc. There are Bayesian implementations of this approach that have been proposed recently. In this literature, they're using what I'm going to call agent-based modeling or iterative learning to study the possible role of learning and transmission in shaping typology. This approach is really different because not only are they looking at the way that learning might shape the distribution of languages, but the language models themselves tend to be really, really simple. And the main reason they tend to be really simple is because a lot of this work is aimed at showing that the putatively innate features from the generativist tradition can be explained as can be shown to emerge from iterative learning. So as you can see, these two approaches are really quite different from one another. Generativist approaches, rich theory of grammar, aiming to explain language typology with the grammar. Here, not much of a theory of grammar, trying to explain typology with learning. The question that we're asking in the research that I'm going to be presenting today is, what is the effect of learning, what is the possible effect of learning on typology when you are assuming a fairly richly specified theory of grammar, closer to what generativists typically assume? And the reason we're assuming relatively richly specified theories of grammar is not because we have a strong position on the innateness of these positions, of these features that we want to defend. It's just that in practice, what you'll notice if you compare these two bodies of literature is that the work in iterative learning is showing that some basic principles of language, like compositionality, you can show that this could be emergent. But when you look at the generativist tradition, the types of things that they're studying in terms of their cross-linguistic distribution, there's just this huge gulf in terms of the set of features that the generativists study compared to the things that have been shown to be emergent. And so for a lot of the features of grammars, it's really hard to judge whether they could be, whether they would emerge from agent-based simulations, whether they might be things that are acquired when you're starting to babble. There's various explanations for how things might come out without being innately specified. So in other words, we take a relatively agnostic approach to whether these features of language are innate or not, but what we want to know is if we do put learning into a model of typology, how might that change our assumptions about grammar when we're trying to do typological modeling with grammar and learning. I just said this in a really long way. If you're interested in this work, I'd encourage you to look at Robert Staub's dissertation. And then I sent along something that some of the people in the seminar read by Elliot Morton and me. This work is related to large streams of previous research. There's been quite a lot of work done on linguistic change with agent-based models. There's a very nice review of that work done by one of the other speakers in this series, Kai Zra, in the Probabilistic Linguistics book. And there's also a fair bit of work that's been looking at the role that learning might play in phonological typology, but most of this hasn't been using agent-based models, and I'll be explaining why agent-based models are useful in this work in a little bit. So, in comparison to a standard generative approach that abstracts from learning, I'm trying to make an argument today that there are reasons why you would want to integrate learning into typological explanation. First of all, if you don't, there are going to be some missed opportunities. So by adding learning to typological explanation, we're going to be able to capture typological generations that grammatical theories working on their own can't get. Both in terms of getting relative frequencies, that's the thing I'll be talking about at the beginning of the talk when I'm talking about headedness and syntactic headedness. Also cases of near zero frequency, near zero attestation. The other thing is that if you are trying to directly infer properties of universal grammar by looking at the distribution over language types, you might be making, and not including learning, you might be making faulty inferences about what the structure of grammar should be because learning can warp the typology. And I'll be giving you an example of this where a particular grammatical theory predicts that certain things should happen, but once you put the learning theory in there with it, you get predictions that these things shouldn't happen any longer. So that's the part we'll get to towards the end. So in particular, the output of our agent-based models are going to tend towards deterministic outcomes and away from gang effects, even though we're working with probabilistic weighted constraint grammars that can represent variation and gang effects perfectly well. Okay, any questions so far? Okay. All this is going to, this is just an overview. So the first case study is going to be about cross-linguistic tendencies towards consistent direction of syntactic headedness. So this is something that Greenberg first noted in the 60s, that languages that have a particular head direction in one phrase type. So for example, the position of verbs with respect to objects, if that's head initial, the verb is the head of the verb phrase. If those phrases tend to be head initial, then other phrase types like nominal phrases where we're looking at the position of the noun relative to like a relative clause or to an adjective, you tend to find that languages that are head initial in one respect tend to be head initial in another. So there's a correlation between the position of the head across different phrase types. And Dreyer has a very nice paper in Language where he looks at the relative strength of these correlations across different kinds of phrase types. The approach to this correlation in standard generative grammar is to say that there's a general headedness parameter that regulates headedness across phrase types. You say, my language is either head initial or it's head final. There's just one parameter that's set, and it regulates headedness for all phrases. But the problem is that this is a tendency. So languages tend to have all of the heads on one side or the other, but within a given language you can find exceptions, and there are plenty of languages that have mixed headedness as well. So it's hard to know exactly how this general headedness parameter is in fact accounting for the tendency without some theory of how you go from the general headedness parameter to tendency. And in fact, what I'm going to be trying to show you is that when you do have a general headedness constraint and learning, you get the tendencies. So here are some data. These are counts of languages from the WALS database. And this shows you the number of head initial nominal phrase types, so noun adjective, noun relative, noun determiner, and a few others. And you'll notice that this distribution is kind of U-shaped, right? You've got a fair number of languages in which all of the phrase types are head final. So the distribution is pushed a little bit this way on this side as well. And this distribution looks particularly skewed when you think about what chance would give you. So if we just flipped a coin for our 6 phrase types, we'd get a binomial distribution, which is in fact peaked in the middle. It would look like that. So this distribution looks different, and across, this is just our count from WALS. These studies have been done quite a few times with different sorts of methodologies. This is a picture from a paper in Lingua, where instead of just counting from WALS, he looked at just 20 languages and looked in detail at the languages. And what you find when you look in detail at languages, that there will often be particular phrases or words that'll be exceptional. So, for example, French tends to have adjectives after the nouns, but then some of the adjectives go before or something like that. So, but when, again, the shape of the distribution, even though we're measuring in a very different way here by looking in detail at individual languages, the shape is got the same U shape. And so that's going to be the target for us, is to get that U shape. This is harmonic grammar with some simple syntactic constraints. And so I'm going to walk you through this table in some detail. For our models, we're just going to have 6 types of phrases. There's nothing in our model that's specific to verbs versus nouns or anything else. We're just going to talk about 6 types of phrases. And for each type of phrase, there are 2 possibilities in terms of where the head can be. Either the head can be in initial, like in a VO phrase, or it can be final, like in OV. So this is 2 tableaux. So for a tableau for a particular phrase type, there are the 2 choices, right or left. And then what you see across the top here are a set of constraints. We have a general headedness constraint, like I talked about a general headedness parameter. Here we have a general headedness constraint. It says head should be on the left, and if you have your head on the right, you get a violation of that constraint, which I'm marking with a negative integer. Same thing, a general headedness constraint, heads are on the right, if the head's on the left, there's a violation. Then for each of the phrase types, there's a specific constraint for that phrase type. Again, the violations, and then the weights are underneath the constraint names. At the right, you have what are called harmony scores. And those are just the weighted sums of constraint violations. So for the top, the type 1 right, we've got -5 plus -2 is -7, right? Okay. Here, the head left constraint has a higher weight than the head right constraint, which prefers left-headedness, and in type 1, that's what we get, because the type 1 constraints are in the same configuration, where the one that prefers left-headedness has a higher weight. And so these scores you can think of as penalties. There's a greater penalty on right-headedness for type 1 phrases. In the other case, it's reversed, because the specific constraint that prefers right-headed phrases has a much greater weight, and a sufficiently greater weight to overcome the general preference for left-headedness headed phrases. And so here we've got a right-headed phrase picked up. So that's how weighted constraints are going to be working for us. And in the simulations I'm going to show you, there are going to be 6 phrase types. For each one, there's the specific constraint regulating headedness position. Any questions about that? Okay. Okay, so just to back up for a second, if we're just trying to get what languages can exist and which languages can't, if we're just want to have a theory about what a possible language is, we could just throw out this general constraint, because with all the specific constraints, we can represent all of the patterns that we find. Some languages have consistent headedness, other languages don't. We can represent them all perfectly fine. Adding this general constraint doesn't change the typological predictions in the sense of trying to generate different sets of languages. But the general constraint does make learning of consistent headedness easier, and it will make languages with consistent headedness emerge more frequently from our agent-based model. So we're going to be assuming a probabilistic version of harmonic grammar called Maxent Grammar. And in this theory, the probability of one or the other type of phrase is proportional to the exponential of the harmony. So here we've taken the exponential of these numbers, and this gives this case 0.95 probability. I'm going to be coming back to this at various times, because here we have a difference between the two in terms of the harmony scores of 3, and a difference of 3 here corresponds to probability 0.95 and we'll be coming back to it. So as you can see here, this is a case where we have relatively peaked probability on this phrase type. Okay. For learning, we're going to be doing gradient descent. And in a Maxent framework, you can formalize that essentially as the Perceptron update rule. So if we have a case where the teacher is saying that the head should be on the right, and the learner expects that it should be on the left, where expects here is we sample from the learner's grammar and generate an expectation. We sample from the distribution defined by the learner's grammar and generate an expectation. We just take the difference between these two. So we have these two vectors of constraint violations. We take the difference, which gives us -1, +1, -1, +1. We scale those by the learning rate and add those to the current constraint weights. And so here the teacher's saying, I want heads on the right. When we take the difference, that gives us a positive value for the constraint that says heads should be on the right. So that constraint weight's going to go up, shifting probability onto phrases that are right-headed. And the other constraint's going to go down, again, shifting probability onto phrases that are right-headed, off phrases that are left-headed. The important thing here is that we're getting a datum from a particular phrase type, but because we have this general constraint, we're making the inference about phrases in general. We're putting more probability on right-headed phrases in general based on getting a right-headed phrase that's a type 1 phrase. As I said, this is gradient descent in the Maxent framework, and Elliot Morton and Katja Percova and I have a paper that just appeared online in Cognitive Science a couple days ago that talks about the connections between this learning algorithm and Rescorla-Wagner, Perceptron, and even the replicator equation from evolutionary biology. So here's learning. This is 1,000 runs, sampling initial weights from a 0 to 10 distribution, and averaging over runs. It's done with a batch version of gradient descent. And you can see this is probability of the forms in the language. So for each of these 6 phrase types, there's a choice between 2. So probability of the correct forms is 0.5 at the beginning. And for the languages with all the heads on the same side, probability shifted relatively quickly onto the correct forms in comparison. So that's 6 heads on one side versus 5 heads on one side versus 4 heads versus 3 heads. And I'm not going to be concerned about whether the heads are on the right or the left, because there's nothing special about right or left headedness in this model. But that's the pattern you get. So it's actually not safe to go straight from a demonstration that one type of language is easier to learn than another to the conclusion that that this model predicts that it should be better represented typologically. There's a nice paper on this by Rafferty, Ettlinger, and Griffiths. One of the things that they point out is that it matters when you don't put all the probability on the language you're being exposed to. It matters where the rest of the probability goes. In other words, it matters when you're trying to learn one language and you don't learn it fully. It matters what other language you think you're learning, and that's going to distribute the probability over languages in different ways depending on where that probability goes. So you need to do something else, and we do a kind of agent-based modeling to generate typologies. We use what we call interactive learning. So in interactive learning, what we do is we have just 2 agents. In every trial, we pick one of them randomly as the teacher, and the other one's the learner. Then we pick one of the phrase types at random, generate a learning datum by sampling from the distribution defined by the teacher's grammar. Then the learner generates its expectation by we sample from the learner's grammar to get the expectation, and then we do a weight update. And we repeat this some number of times and take the final state as being the language. So you can have, and then after you've done this a bunch of times, you've got a distribution over languages that you can then compare to the distribution over languages that you find in the empirical typology cross-linguistically. One interesting thing about these models is that they tend towards assigning probability 1 to one of the candidates. They tend towards a deterministic choice, even though and the reason that they do that is because, well, first of all, when you have an update, you can either move closer to assigning probability of 1 to one of the candidates, or away from that, of having equal probability on the 2 candidates. But as you move into the weight space where you're assigning high probability to one of the candidates, your weight changes are going to happen less frequently, because that's the place where you're agreeing that one of the cases is better, and so you're not going to be having an update. And then the other thing is that when you're in that space in this particular model, because we're using exponentiation, the weight change corresponds to a smaller probability difference the closer we get to assigning probability 1 to the candidates. So in other words, as you get to closer and closer to assigning probability 1 to one of the candidates, you tend to stay in that space. So the system spends most of its time in deterministic states. So what we do then in our simulations is just stop them when they get to probability 0.95. And when we've looked at what happens if we run them longer, they tend to stay there. If we had chosen instead 0.75 and we've tried that, it doesn't really change much. So, yeah. For those of you who are familiar with the other models of iterated learning, this is, in a sense, the polar opposite of what Kirby and Herford or Griffith and Kalish do. They have what you can think of as purely generational learners. They also, like us, they have 2 agents. But at any one time, one's the teacher and is giving data to the learner, and the learner is learning from some number of trials. and then that learner becomes a teacher, and you have another generation, and so on. Ours is purely interactive in that each agent has the same probability of being the teacher and a learner. And reality is actually in between these two things. So when people have looked at language change, and especially language change that's happening now, that you can study, you see that it looks like it's not just adult to child transmission that's important in understanding language change. It's also important the structure of, say, adolescent communities, which is things we find in, say, Penny Eckert's work. So neither of these models is very realistic. If we want to have a really realistic model that have some aspects of both, then we probably have more than 2 agents as well. But we're using this model just because for us it's simpler to generate typologies this way, and in an ongoing work we're thinking about the differences between these types of models. I should say that if you're interested in iterated learning models, this Dediu paper is a wonderful overview, and he talks about some of the differences between the different kinds of network structure. I should also mention that all the references for these slides are on the presentations page of my website if you're looking for the references. Okay, so this is what happens when we run that agent-based model. We get the distribution that you see in red. This is when we sampled from a 0 to 10 distribution, stopped with 0.95 probability of one of the candidates. This is an average over 1,000 runs. And we're getting more probability on consistent headedness and less on inconsistent headedness. This is the data from the nominal phrases. As I say, it matters exactly which phrase types you choose and so on, but what seems to be consistent is this Klein, and here I've given you the chance distribution to show that what we're getting is different from the chance distribution. Okay, so this tendency towards having consistent headedness is coming just because we've got this general constraint in the constraint set. If we took it out, we'd go back to a chance. There's not an explicit bias for having consistency or headedness, it's just we've got this constraint in the constraint set. We started at 10 after? Yeah, okay. And the reason this is happening is partly because of the dynamics of learning. So the updates are targeting both the specific and the general constraint. So as I mentioned before, you're generalizing from each specific instance. Also, because of the distribution of different kinds of languages in the weight space. So consistent headedness becomes more probable when you have relatively low weights, but at the same time, you want to have high probability on one of the candidates, because high probability on one of the candidates means that you've got a relatively high margin of separation between your two candidates, and to get that high margin of separation, you need relatively high weights. And so now you can see that this creates a tension, and so, yeah. So, and in particular, it creates a tension because if you're trying to learn one of these languages that has inconsistent headedness, because if you're learning the language that has consistent headedness, then you can just you can get 0.95 probability on one of the forms in each of your phrase types by having weights of 1.5 on the general constraint and each of the specific constraints. 1.5 plus 1.5 gives you 3, gives you this difference of probability. But if it's inconsistent headedness, then you have to have, on at least one of your specific constraints, you're going to have at least weight of 3. So that's why the distribution of the languages depends where you are in the weight space in these cases. These results are probably very generalizable. So they would generalize to other cases that you would represent with constraints in this sort of specific and general constraint, specific and general relationship. I would guess that this result would generalize also to well, for one thing, these Maxent models can be used with derivational theories. So a lot of approaches to syntax are derivational. You could use these particular models with those grammatical theories, and I think that the basic result will probably generalize to other grammatical theories, learning models, and network structures. I think it'd be very interesting then to look at the specific predictions that you would get out of each one and how they would differ. Okay, so why doesn't everyone use weighted constraints? I guess you've gotten some of the history of this. I've been talking with some of you about this morning. But in linguistics, there is a model of constraint interaction called optimality theory, which is hugely popular, and which was developed by Alan Prince and Paul Smolenski in 1993, a few years after Paul Smolenski had just proposed a weighted constraint model of grammar that he was calling harmonic grammar. But when he started working with Alan Prince, they very quickly decided to switch from a weighted constraint model to a model in which constraints are prioritized by ranking. And the reason they gave for doing this was that the typological predictions of a weighted constraint model were just wrong. That you would generate languages that don't exist amongst the world's languages. And it's a little, when I started looking into this, it was a little frustrating because even though they say that the predictions are wrong in their book, in the book they don't give any examples. And when you look at the literature, there aren't a lot of them, which is not to say that they're not correct. In fact, I think for particular kinds of constraints, you might generate some pretty weird things with weighted constraints, but there aren't a lot of concrete examples you can find in the literature. One of the concrete examples that you do find is in a paper by Legendre, Sirac, and Smolenski in their Harmonic Mind book. They give the example of what are called stress windows. So now we're back to phonology. In a stress window, this describes a case where, so stress, we're choosing one of the syllables in the word to have stress. There are many languages. English has what's called iterated stress. So we'll have a word like Apalachicola where there's a main stress and then a couple of secondary stresses. We're going to be just talking about having the possibility of just having one stress in the word. And in English and lots of other languages, particular kinds of syllables are better stressed syllables. So in English, you have words like agenda that have a closed syllable that gets stressed, as opposed to Canada, which doesn't have the closed syllable. So we put stress on the penultimate syllable if it's heavy, as an agenda, on the anti-penultimate stress if the penultimate syllable is light. This is a toy example that's sort of like that. This is a 4-syllable stress window. So we have two constraints. One constraint is weight to stress, says if a syllable is heavy, if it ends in a coda, it should be stressed. So it's satisfied by this case, bantalama. It's hard to pronounce because it's not English. Bantalama with stress. Bantalama violates weight to stress. Then we have another constraint that says stress should be at the right edge of the word, and it's violated by every syllable in between the stress and the right edge. So this guy's got the stress right on the right edge of the word, doesn't violate this alignment constraint. This one has stress on the heavy syllable, which is 3 syllables away, violates the alignment constraint 3 times. And I set up the weights here such that in this case, where you've got that heavy syllable 3 syllables away, you put stress on the heavy syllable. But in the second case, where we've now got the heavy syllable 4 syllables away, you put stress on the final syllable. Languages like this, where you have a window at one edge or the other edge of the word in which you'll go and find a heavy syllable to stress, they exist. But there are no languages that have 4-syllable windows. And so Legendre et al. Point out that with weighted constraints, you can get a 4-syllable window, you get a 5-syllable window, a 6-syllable window, a 7-syllable window, a syllable window up to any size you'd like by getting the right ratio of weights between these two constraints. And they say that this type of behavior of weighted constraints is why you wouldn't want to use weighted constraints in modeling typology, because you're going to generate, well, in this case, an infinite number of languages, an infinite number of unattested languages. So here are some data on stress windows. It's correct that 4-syllable windows don't exist. This is from a paper by René Copper. Shows you languages with final 2-syllable windows, final 3-syllable windows, initial 2-syllable, initial 3 syllables. Apparently there are a couple more cases of these besides the ones in Cogger's paper. But what you'll notice is not only that our four-syllable window is absent, but there's a big difference between final two-syllable and final three-syllable, initial two and initial three. That is, two-syllable windows are more common than three-syllable windows. So why should this be? Why should it be that two-syllable windows are more common, three-syllable windows are slightly less common, and four-syllable windows are out? The alternative to harmonic grammar, optimality theory with rank constraints, actually with the constraints that I was showing you before, it can't generate any stress windows. So if you have one constraint that says I want my stress to be on the right-hand side, if that one's ranked higher, you have stress in the final syllable. If you have another constraint that says I want to stress heavy syllables, then you'll go as far as you need to find a heavy syllable. With those two constraints, you can't even get a stress window at all. So in Kochler's work and other work, they have more enriched constraint sets that allow them to get stress windows. But Kochler's work and no other work in OT, even though they might get you the difference between a three-syllable and four-syllable window, they don't get you the difference between two and three-syllable windows. They don't give you probabilities over languages in this way. There's an old paper by Alan Prince called In Defense of the Number I, where he's looking at Goldsmith and Larson's dynamic linear model. And that model also, it's a different kind of weighted constraint model that I'm talking about here, but it can also give you stress windows of any size. And what Prince points out in this paper is that learning might give you an answer to the question of why you don't find such languages, because as the windows get larger and larger, the ratios that you need between the constraint weights get finer and finer and might be harder to find in the weight space. So here, what I've done is just shown you, with these two constraints that we're working with here, the proportion of the weight space that's taken up by different window sizes. So here, if we sample from a uniform non-negative distribution, and we just take the case of which of the two possibilities for each of the tableau has the best, highest harmony or highest probability. One syllable windows, that is, stress is always on, I was using a line right, well, it's not, yeah, line right. Stress is always on the right-hand side. That has half of the weight space, because those are all the cases where that constraint has greater weight than the other one. And then all of the other language types are cases where weight to stress has sufficient weight that it can overcome this constraint, but then it has greater weight. But then these other cases are ones where like two violations of this one is greater than or sorry, yeah, two violations of this one are greater, three violations, four violations, and so on. Again, it matters if we want our candidates to have quite a lot of difference in probability. We have to have a difference of 3 between the two. And again, if the weights are forced to remain relatively low, we squeeze out some of the gang effects. And so you get distributions that look like this. So here we've got, when we sample from 0 to 20 or 0 to 30 distribution, I mean, the take-home message from all of this is that there's a much less space for in the weight space. The larger windows have much less probability. One thing I should clarify here, what 7+ means. So we're considering words up to 7 syllables in length. There are 8-syllable windows, 9-syllable windows, 10-syllable windows, but as long as your words are up to 7 syllables, all of these things mean that you'll stress a heavy syllable no matter how far away it is from the edge. This brings up the other factor about stress windows and learning. There's also less evidence for the larger windows, so not even thinking about the fact that you have a Zipfian distribution over word lengths. If you just think about the fact that for a 2-syllable window, in order to see that there's a 2-syllable window, you need words that are 3 syllables in length. Because you'll see that you put stress on say the penultimate syllable, not the antepenultimate syllable. For a 3-syllable window, you need words of 4 syllables in length. So the 2-syllable windows, you get evidence from the 3-syllable words, the 4-syllable words, the 5-syllable words, you see what I mean. So I'm going to show you learning simulation that had all the combinations of heavy and light syllables for words up to 5 syllables in length. I'm going to measure success in learning on just the critical forms, like for what I'm calling the 1-syllable window, where stress is always on the edge. This is the case where either you put stress here and violate weight to stress, or you put stress here and violate the alignment constraint one time. And I'm doing it now on the left side. LH versus LLH for 2-syllable, put stress here, but not here. 3-syllable here, but not here. So that's how I'm measuring accuracy. And yeah, probably not surprising at this point, stress on one edge is a little easier than a 2-syllable window. 3-syllable windows are harder than those guys, and 4-syllable windows are the hardest. This is the agent-based model run like the other one that I showed you earlier. But now we're looking at words from 2 to 8 syllables in length. We're using a standard OT constraint set, which has many more constraints than the ones I've been talking about so far. We start by sampling from a uniform distribution from 0 to 20. And what you see is that you get, these are the languages that have stress on one side, either left or on the right. You get 2-syllable windows. You get 3-syllable windows, but out of 10,000 runs, there were no instances of 4 to 7-syllable windows. And then these are the languages that will go all the way to 8 syllables to put stress on the other side, which occur, like in the sense of languages in which they're called unbounded, unbounded default to same languages. They occur, although probably not with this high probability, but. So in terms of the stress windows, the results of our agent-based model get you gradient differences in frequency between language types, just like the real typology. The notion that our grammatical system does not generate something is replaced by near zero predicted frequency, 0 out of 10,000. I mean, there's still some probability on it. If we ran enough runs of our agent-based model, presumably we'd eventually get a 4-syllable stress window, but. So there really isn't any problem with harmonic grammar in this setting once we've incorporated learning in an agent-based model. So it's, in terms of thinking about what's called harmonic grammar, the weighted constraint systems versus optimality theory, we've got this grammatical system that uses weighted constraints but skews away from gang effects. And Coral Hutto has also been working on another example that looks similar. There's a lot that you'd want to do in terms of understanding how general this result is, whether it really does get rid of the typological monsters that people are worried about when they use rank constraints rather than weighted ones. But the consequences are pretty striking because from the perspective, what we're trying to do when we're doing generative linguistics, part of it is trying to avoid over-generating languages. We don't want to generate languages that don't exist. The grammatical model alone might overgenerate, but then when we take into consideration learning in our full model of typology, it remains sufficiently restrictive in terms of getting the typology. Okay, so like I said, in generative linguistics, typically what we're doing is making relatively direct inferences about the structure of universal grammar, about the structure of grammars in general from typology. But the results I've shown you here and related ones, I think they suggest that if you abstract from learning and doing this, it's not entirely safe. So as I mentioned relatively quickly, the probabilistic grammars that we're assuming when they're cast in an agent-based model, we're tending to get peak probabilities, tend to get deterministic outcomes. We're getting skews away from gang effects. And the other problem with abstracting from learning is that you're missing opportunities. You're missing opportunities to account for the tendencies that we find rather than just exists or doesn't exist. As I mentioned before, those general constraints that people propose for syntactic headedness, in terms of just accounting for what exists and what doesn't, general constraint isn't actually doing anything. But in the learning model, it does exactly what we want it to. We're in the full model. Okay, so that's it. Some thank yous. Thank you.